So with this, our next talk is going to be overview of OSU INAM deployment at OSC, and there will also be a live demo. So we have two speakers for this session. Heechang Na from OSC, he's a senior scientific applications engineer at the Ohio Supercomputing Center. He's interested in performance analysis, system monitoring, and research environment development. So he has a PhD degree from Indiana University. And before joining OSC in 2015, he worked with Milk and HP QCD collaborations in Lattice QCD. The second speaker is Pouya. Kousha. He's a fifth-year PhD student at Ohio State University. His research interests are parallel algorithms, distributed systems, high-performance computing, and real-time scalable profiling tools. So with this, I invite Heechang and Pouya to please start their presentation.
Okay, thank you for the introduction. Okay. Oops. Okay. Oh, you don't see the screen, right?
Yes, we do now. Yeah, we see it now. Yes, we see it.
All right, but it's not presentation mode, right?
No, not in presentation mode.
Okay. So why this is so?
That's fine.
Okay, can I just continue with this?
No, I think please click present live. This third option.
Okay. Present live is the key.
No, that's fine. It's I think it was just downloading from OneDrive or something. We actually see a black screen now. If you have multiple screens, then you might want to switch.
Okay. Just
or you can download these slides to your local system and then present instead of, you know.
Yeah, okay, I will try that. Sorry for that. Okay. Where I can download it.
If you click on editing.
This OneDrive thing is very new for us.
Yeah, could you please
So
click on editing?
may I suggest something? Just open your Microsoft application on your desktop.
On my desktop?
Yes, please open it on your desktop. Open the Microsoft application on your desktop.
PowerPoint?
Yeah. Yes.
I did.
So let's wait for it to come up. So when it comes up, please go to File and Open.
Oh, okay. I tried to open it from this OneDrive thing before. Okay.
Yeah, that should be the one. So please, yeah, grant access. Just click on grant access. Now you can present it from here.
Okay. Thank you for the help. All right.
Sure.
Let's just start it. So today I'm going to talk about the OSU INAM deployment at our center, Ohio Supercomputer Center, and we will show some live demo. So I and Pouya will present the talk and the demo, and the tray is available on the Slack channel for more detailed question about the technical aspect on the deployment. So this is my outline. So I'm going to talk about the infrastructure of our center, and then Pouya will cover the OSU INAM. And then I'm going back to talk about the INAM deployment at OSC, and we will have live demo, which is the highlight of our talk. Okay, so our system consists with two clusters, ONS and Pitcher. So ONS we have in 2016, and we have Pitcher with two separated deployments. First, we got a Pitcher in 2018, and then we got the expansion in last year. So they share very similar architectures, but they are slightly different. For example, the GPU, they are all the same V100, but the old Pitcher has the 16 gigabyte memory, and the newer one has 32 gigabyte memory. But essentially, these Pitcher and Pitcher expansion runs with a single Slurm instance. So we consider this as one cluster. And we have disk storage, which is this home directory, and then two different GPFS directory for the project and scratch space. And those are all the infrastructure is combined with a single integrated InfiniBand fabric. We wanted to keep maintaining with a single fabric because we wanted to provide a consistent file system that the users can access from any clusters. So we have 109 InfiniBand switches for the 1,544 hosts, which include compute node and other storage servers and web servers and other things as well. So we have, so because we covers multiple generation of the hardware, so we also have multiple generation of InfiniBand, ConnectX 4 and 5, EDR, and we use UFM and rough chains for rough chains tools for maintaining our configurations. So this is fabric topology diagram that we pulled from the INAM directly. So blue dot representing the compute node, and the red dot represented the switches, and the lines are the links. So we have three level switches systems, so that the level three switches in the center place, and the level 2 is placed on the center of each cluster. So this cluster is showing for the Pitcher and the Pitcher expansion, and these two clusters representing OS. We have separated cluster like this. The difference is that these smaller cluster are GPUs and higher memory node. So that this one has lower over subscription ratio than this part of OS. And those are smaller clusters are the storage and the other servers that is corresponding login node and such other services node. So this is overall the structure of OSC. And then Pouya will talk about the OSU INAM.
Yes, could you please go to the next slide? So this is overview of OSU INAM. So INAM is a network monitoring and analysis tool that to collect the traffic from various levels of HPC, including application, MPI library, Java scheduler, and also IO together and gather all of these information remotely so we can present node level, job level, and process level information. We gather all of this at real time, so you can see live or historical view of your network, job, or set of nodes that you like. And the key feature here is that all of these are gathered sub-second in some cases. And INAM is all publicly released, and it's been downloaded more than 5K times over the lifetime of the project, and it's being used at multiple HPC centers. On the right, you can see some of the features for OSU INAM 0.96. You can also see the QR code to go to the download page and see the features for OSU INAM. Next slide, please. So overall, we have the HPC stack on the right side that I mentioned, the 4 layers. And OSU INAM have 3 components. One is the red one, OSU INAM Daemon, which has 5 subcomponents in it that gathers information from various levels of HPC. And then we put it onto storage, and then goes through this real-time goes through Spring Server and the web UI. Heechang, would you please click on the, yeah. So all of these are gathered like in a live manner. Also Fabric Discovery and Port Metric Inquiry, that is for discovering and inquiring IB Fabric encounters happen at real time. Next slide, please. So we also provide a best practice set for dedicating resources, because INAM would run on one node. So you've got to know like how many threads you want for each component for the daemon part. And we have a set of best practices to dedicate resources for each subcomponent of OSU INAM daemon. For this case, for OSU, since the cluster size is more than 1,000 nodes, you see that the resource allocations are in bold. Another aspect that we studied on OSU, and we have published it in our PERC paper, is the load balancing of all of these components among each threads. And if you look at the figures on a general view, you see that the balance between all the colors are the same. There are up and downs, but there is no like a thread, like a core that is not used. Next slide, please. So that brings me to the end of like INAM overview. Heechang, if you want to take control from this point.
Yeah, thank you, Pouya. And then I'm back to talk about the INAM deployment at OSC. All right. So we are INAM project collaboration. So we work together, and we are conscious of OSU and OSC workforces. In OSC, we have Troy Dokendorp, me, and Karen Tomko. We have been working with OSU to get INAM make it better since 2017, and the collaboration completed in last year. INAM has been running at OSC on production system for more than 2 years. When the OSU developed a new version, and iteratively we tested and deploy that new versions on our system, and we do the iterative cycles to make it improve. Okay, and this is the configuration of on OSC. So currently INAM configured for Slum, but previously we used the Torque and MOAB as well. So in fact, when we migrate from the Torque and MOAB to Slum, we had the 2 resource managers at the same time, Slum and Torque and MOAB on INAM. and that was working just fine. And this data collection parameters is tunable parameter. We choose to collect the data every 30 seconds, and we keep the job history for 1 week. And the database size is about 70 gigabyte. And then MVAPICH 2X integration is enabled. All right. And what impact that OSU OSC collaboration made on INAM. So first of all, we improved the performance. So before we bring INAM on our larger fabric system, the rendering time for the diagram was not noticeable on a small lab fabric. But when we bring it on our system, that the rendering time is significantly longer, so that the time rendering was taking more than 2 minutes. And the OSU group work on it and make it rendering in multi-thread, so that it achieved 50 times reduction in the fabric discovery time. And we made a database optimization for many aspects, so that we tuned the database parameters so that it can execute much faster. And then we make the MySQL services restarted automatically, so that it's more stably working. And we improve the installation and configuration features, so that it can be installed and configured more easier, at least for our center. So now it is provided as a single RPM with all components. And we, from the iterative process, we have improved user interface and a couple of, identified the bugs on that. So more information you can find out from this website, and we had a publication from Pouya for Part 21. Okay, so we will go into the live demo. So I'm going to show the network view of OSC cluster, and then Pouya will cover more detailed features that INAM can deliver. Okay. All right. Okay. All right. So this is the main page of INAM. INAM is a web service. So we see it from the web browser. And the thing that I like to show is the network view here. So it is rendering. So this is a live view, so that please understand if you need to wait little time. So it is rendered. So this is the entire fabric diagram that I show you, something similar diagram that I show you, in the presentation. So blue dots are compute node, excuse me?
Yeah, can you go to the full screen so that all the features are shown clearly?
I figure that this is the best screen that I can show you. If I make it full screen, and then it will show like this part, because it's wider. So anyway, so if I hover over one thing, and then it shows the information, lead, GUID, name, and job ID. So, and this is the ON cluster. If I go on over here, so that the name starts with P, so that I know that this cluster is for the pitcher, and the job ID is 49965 29 so that I know that this job is currently running on this particular node. And then I can do right click on it and then open node info. And then it shows the current node information on the system. Pouya will show more detail in his demo. And we have various features within this network view. We can filter by complete network and the job ID. So job ID, I can put the job ID. And then it's showing only the component that is related with that particular job. So this is just a 2-node job, so that there is a 2-node and the one switch related with that. And I can do on the historical view. Yeah, on the historical view, I can actually play the job, the network status. So if I click it, and then you see that the time bar is progressing, and you see that the status is changing in time. All right. Then getting back to the total network view, 2 more things that I like to show is that the link usage. So it shows the overall link usage status of entire network. And this one is shown in this color-coded diagram. So 95% of link is used in 0 to 5% of the usage, and about the 5% is used by 5 to 25%. So if I click it, okay, I can remove and show only these 2 things, and then this color is actually represent the corresponding link, so that I can magnify it, so that I can check which link is actually using more traffics. And I can search each node using RID and name here. I can search for P0123 and find the node. And you see that this highlighted one, this one is the P0123 node, so that you can search. So this is what I have prepared, and then Pouya will take over so that he show more detail.
All right, thank you. Okay, can you guys see my screen?
Yes, Pouya.
Okay, thank you. So for this one, I'm gonna go over a historical graphs. And for this one, we show a job ID that was running on 16 nodes, running milk application. And we choose the start time and end time mentioned here. So when you reload the job and click on this one, it shows you the start and end time. For this one, we see that the job information here, like when was the start time, what nodes were involved in this job, and you can, same way on the live view, you can open the nodes here and, for example, see like the process counters and every other information the same way as we have here. So going forward, for this graphs here, actually, they show the CPU and memory usage for all the nodes participating in this job. And you can view it on the job level and also the node level. This feature is enabled on runtime and also for historical. Same thing for node level view. So you can see like what is your VM size, VM peak, and VRMs, and how much CPU were used for the user of that node, which were the user and the percentages. The other two graphs are internode communication buffer usage, the VBUFFs. And again, it's available on the node level and job level. They are supported. They are supported for process level if you go to the node level page. Then since last year, we added a bit of more information for MPI operations that are happening. So we included global MPI internode and intranode data exchange. That includes point-to-point collectives and RMAs. And we break it down into like buckets of message size. So if you want to notice like what is your dominant message size being used for this application, if you look here, you notice that for non-blocking, we are sending 33 terabytes of data between the message size of 8 kilobyte to 64 kilobyte, and that's happening between internode. We also have internode amount for the amount of 23 terabytes for the same message range. So, and the next message range that is being used mostly is 2 kilobyte to 8 kilobytes. So that gives an understanding to the application developers and like research scientists that when we have optimizations, it's usually like about like choosing what optimization for what message size, and they can apply the optimization for the specific message range that they're looking for. Going forward, we have provided the MPI primitive usage. We have a global session that's for the start of MPI init to the end, and users can also define additional profiles. Please refer to my PERC paper for additional information. But over here, I show one chart of like the usage over the time, and we choose 3 MPI collective operations, and you can see through the runtime of the application how much data has been sent on the aggregate, on the left side on an aggregative manner, and on the right side on a delta. That means the difference between each data point, and the color codes are used to figure it out. On this chart here, if you want to understand what, let's say you have an application, you don't know what MPI operations is using, and you want to get an understanding like of what MPI operation you should focus to optimize more. That's where we use this most used MPI primitive. So it shows the MPI primitives used for different metrics like time taken, count sent, count received, and on different levels. So, and one more thing, it shows you the PVAR, the MPIT performance variable associated with it. So that gives you an understanding of like what is the algorithm being selected, or what PVAR you should look into to query. If you click on one of these, it's calculating, okay. Then you can see that for all reduced, what PVAR is used, and more importantly, you can see a breakdown of message sizes, again, like buckets, I call them here, for each of the participating nodes. And if you roll over it, it shows you the total time it was taken. So it's, for this one is 110 seconds, and for the count of 1,000,000 here. So it shows you the performance variation and the small message range size for all reduced across all of your nodes. So we have like from numbers from on average 79 microsecond to 118, and the count is the same. So that might define the performance variations that you see on the network. Going forward, we also provide job level counter statistics. There are different metrics available here that you can choose from XMIT data, that is the IB level packets, these are like the MPI level collective byte sent and receive, RMA, IO, CPU usage, and virtual memory usage. We also have the node level information. So I choose here CPU usage for one of the nodes here. It's mentioned this node, this is a GUID, and it shows you the read interval for how long are the data points, or like the distance between the data points. And this way you can monitor the CPU usage of your node during your job. Another feature that I add, like this is purely like MPI level information. Shared memory processes like byte sent. So it shows you on the internode like how much data has been sent through the shared memory process. Again, we have two axes. One is aggregate, one is delta. It's the same through all of our charts. And finally, I have another node that shows the IB level counters for transmitting the data. And you can see like what is the pattern being used here. One keynote is that we only show a few data points if a user is interested to get we collect this at 30-second interval. So if you like to be more exact into like having more data points, you can choose a time like smaller chunks and show you that. This feature to show only limited number of data points is to be able to process and like not exhaust you with so many data points. And these are the other nodes that you can just like open to see the transmitted information and choose a metric. So this is our MPI level, and then going to the IB level, you can choose which nodes you're interested from the participating nodes in this job. And you can see some basic stats for the node, like what is the LID, GUID, what switch it is connected to. So this can be useful, when, for example, if there is another job running on that switch and that might impact the performance. For that, as we mentioned, you can use these filters to figure out like what are the congested links. So here I'm showing the IB level information gathered from the IB itself, and you can see the unicast, multicast, also the errors, if there are any errors, it would show you. So we noticed that there were some symbol errors happening on this link at this time. So that's how you figure out like if there are anything happening for your job. And that's pretty much it. The same level of information and charts are available if you go up here and choose a node. So here you can see the most primitive MPI used for processes. So if you choose all, that shows you like amount of like this one index is the process rank. Sorry, this is the process rank, and this shows you how much it has sent information. So yeah, that's all I have here. I'll be happy to take any questions.
Any questions from the audience? Any comments?
There is a comment on the Q&A.
I don't see anything. Also, if you like a full tutorial for OSU INAM at your like center or something, we are happy to provide that.
So the question reads, for job level statistics, are the jobs sharing the nodes supported, or is the requirement that nodes are allocated to jobs in exclusive mode?
Right now, we require that the nodes are allocated in an exclusive manner.
Okay, and another question is, I noticed at the beginning, INAM now has Lustre support. Does that use Lustre job stats feature or some other mechanism?
What? What was the question again?
I
What's
noticed at the beginning, INAM now has Lustre support, Lustre, the file system.
Oh, yeah.
So does that use the Lustre job stats feature or some other mechanism?
We gather the information by accessing the Lustre file information on proc file system. So that
So,
for
we get the client information from the proc file system and the server information directly from the metadata server. But the job stats is something we can definitely try to use going forward. That seems a much cleaner way. Thank you.
So on OSSC, we don't have Lustre systems, so that it was not tested.
Yeah.
Questions, comments? So if not, let's thank again Heechang and Pouya. Thanks for the presentation and the demo. We are running around 20 minutes late, so let's go to the final session, which are the short presentations.